I'm sorry, but I need to begin this discussion. Uh, I mean, just from the from the first slide, uh, because it hasn't been covered in section B and C, but I covered a few slides with section A. So, section A, folks, please bear with me a few minutes until I can catch up where you are. Well, in this discussion, we'll basically explain the operation of radio broadcasts, uh, but an underlying technology, superheterodyne principle, will explain as we do that. And the I mean the key purpose, you can say, is to explain this particular technological concept. It's very simple. It's because this principle is useful, uh, but the radio broadcast system is not very important. Well, uh, it is. It has two sides, AM and FM, amplitude modulation and frequency modulation. The AM side is getting obsolete, but the FM side is not. So I shouldn't put it this way. I mean, it is not. It's not. No, I shouldn't say it is unimportant, but it is not as important. It's also true that it is not as important as it was before. Okay, so let's go through it. Um, the AM and FM radio, we all know that it uses different frequency chunks for the transmission of different radio stations. Um, and we, as the users, we tune to the center frequency of a particular channel. Uh, and these days, most of you probably have used only FM. AM has already very little use. Now, there are some geographical region definitions which differ in how they are used. But we also need to, and before I discuss that part, we need to understand that the audio, what do you mean by audio bandwidth? Is the bandwidth of our audio signal. In radio broadcast system, it includes only audio information. So the information takes up some frequency range, which we are calling audio bandwidth, and that is modulated on a carrier either using amplitude modulation or frequency modulation. Now, this audio information basically involves two things: the human voice, which is called here speech, and also music. It may have music. Well, the uh, human voice frequency components lie within 20 kilohertz, and our audibility is also up to 20 kilohertz. Some animals have it different. Ours is the same. We can pronounce up to 20 kilohertz, and we can also understand or listen and understand up to 20 kilohertz. However, and to understand how we get the frequency components, actually our voice uh, exerts some air pressure, and which could be converted to electrical signal using a microphone in multiple ways. A simple understanding is like, say, if you have a diaphragm in front of you, and the diaphragm moves depending on the air pressure as you speak. And this diaphragm can be linked to one side of a capacitor. So the capacitor thickness or the spacing between the capacitor plates vary as you, it's depending on the air pressure. So your uh, speech exerted air pressure variation is converted into the capacitance, okay, because of change in the spacing between the plates. And if it is a part of a circuit, then the current would also vary accordingly. So the current variation will reflect the air pressure variation. And this current variation, if you decompose using Fourier transform, you get all the frequency components. The frequency components will be within 20 kilohertz. However, it can be found that the most powerful components, the components with significant amplitude levels, lie within 4 kilohertz. In fact, it is even lower, is around 3.4 kilohertz. So most powerful components lie within 3.4 kilohertz. And this signal should first pass through a filter, and then you can use it as an information uh, for further processing in the communication system. Always the information is given a particular bandwidth for the process in communication system. It will work with certain information bandwidth uh, mm, uh, that is specified. Now, so this is why a filtering must precede. This filtering goes up to, usually goes up to 4 kilohertz using the filter slope. So the actual rate audio information has significant components within 3.4, and then the additional 0.6 kilohertz is left for the filter. So there is no ideal filter, so you'd have some filter slope you need to allow. So up to 4 kilohertz you can consider uh, as the overall filtered signal for the process in communication system. Okay, however, this 4 kilohertz filtered signal is good enough to carry the voice information, human speech. It cuts off the high frequency components, but when you reproduce, you cannot probably recognize the changes, because as I said that beyond 3.4 kilohertz, the components have very low power level. So most of the significant components lie within the. So after reproduction, the reproduced signal is a good replica of what you had earlier. You have captured all powerful components. So it is fine for human speech, but some musical instruments generate significant components beyond these frequencies. They have powerful components even at high frequency. I mean, high means up to, is typically up to 15 kilohertz. So since our audibility supports up to 20, these components are important when there is music. I mean, especially from those kind of musical instruments. Okay, so the audio bandwidth is taken around 4 kilohertz for, uh, I mean, in AM radio broadcast system. But if in FM, this audio bandwidth is taken up to 15 kilohertz. Here W denotes this audio bandwidth. So you can see that for FM, it is 15 kilohertz. The total bandwidth after demodulation would be larger. For AM, it uses double sideband, including the carrier. You probably remember that you can have, I mean, single sideband communication or the communication with suppressed carrier. These are also possible solutions. But amplitude modulation radio broadcast system uses double sideband, including the carrier. So the total bandwidth will be twice as much as your W. Probably you are understanding that if you have a single tone, I mean, just a sinusoid, okay, maybe say with frequency 2 kilohertz. So when you modulate as AM, so maybe say on 550 kilohertz you are modulating. So you'll get three components at 550 kilohertz. 552, and 448. Okay, but your audio information will have many frequency components with the maximum 4 kilohertz. So after modulation, you will get many frequency components around this 550, but with a maximum 554 and with a minimum 446. So there will be many components around, but the maximum and minimum will be additional 4 and uh, 4 less from your carrier. So the total range will be 4 plus 4, 8. So your bandwidth requirement is twice 2W. This is for AM. For FM, it is little larger because you may remember that you get many after when you just modulate a single tone, a single sinusoid, a single frequency information, you will get many components after modulation as given by Bessel function. Uh, so there'll be significant components over a wider range. You can ignore the low power components, but still you have to cover much wider compared to AM. It depends on how precisely you are capturing. And mm, in the case of FM, they go up to 200 kilohertz, 100 kilohertz on each side of the carrier. So you see that it is much larger. Okay. Well, by the way, I was little mistaken even in this slide. It was 4 before. W uh, for F for AM, I said about 5. About 5. Yeah, yeah, yeah. It's all right. It's correct. So it is W is has okay, let me go through these slides first. ITU has different regions um, for the world because there is some difference in the trend how people uh, set different values, and we fall in the ITU region 3. Uh, ITU region 2 is America, which goes differently. Okay. A lot of times ITU region 1 and 3 has similar operation. Okay. So you see we are in region 3, the pink part. For radio broadcast, ITU region 1 and 3 has the same kind of operation, but 2 has difference. Like W is taken for AM 4.5 in ITU regions 1 and 3. So the total bandwidth is 9 kilohertz. It was previously actually 4 kilohertz. Later they extended to 4.5. So there was 8 kilohertz bands. Uh, but for ITU region 2, it is always 5 kilohertz. And so the total is 10 kilohertz. Uh, it goes little higher than 4 just to capture the music better. Uh, the channels now in ITU region, it was different before when we had 8 kilohertz. Now the different channels are available within the frequency range 526.5 through 1606.5 kilohertz. So AM radio must be transmitted using some channels from this region, from these ranges. Um, and the center frequencies are where we tune, and they are 531 to with every 531, then 540, okay, at 9 kilohertz spacing. For IT region 2, since we have 10 kilohertz, the numbers have been always the same. The range is 525 through 705, and the center frequency is 530 through 530, 540, this way on and on. For FM, is the same everywhere in all IT regions. The total frequency range is 88 to 108 megahertz. And you know that the audio bandwidth is larger, 200 kilohertz. So to accommodate this larger bandwidth, you need to use high frequencies. Uh, Unlike AM, which is just a few kilohertz, a few hundreds of kilohertz. Here you need operation in megahertz range. The difference is that with AM, well, I should not say in the beginning. I say that AM is getting obsolete. Probably it is not. It's not getting obsolete. Its use is getting more and more limited. This is true. Neither AM nor FM is getting obsolete. There will be some use left, okay, even in future. It's because AM with its very small bandwidth can operate at low frequencies. See, the carrier frequencies are very low. So you can cover a very wide range. Like in 1971, we had Shadin Bangla Betar, and it was transmitted from somewhere, furtively. Okay, the opponent couldn't identify where it was transmitted from. But it would cover the whole country, okay, because these low frequencies, you can have wide, very wide coverage easily. With FM, you need multiple transmitters, okay, because you are already at pretty high frequencies. And FM, no, the whole radio, the use of radio broadcast is getting more and more limited, you know. But FM will have significant uses in other areas, like the army uses some communication system among themselves, dedicated communication, and most of the time they use FM radio. Okay. Uh, we also have Bangladesh Army also has some unit. During war period, they're supposed to carry some communication system, every soldier, and it uses FM radio communications. Okay, and the advantage of FM over AM, probably you remember. I'm just touching upon it because this must have been covered well in the first communication course. You spend most of the time on AM and FM, I know. But just to help you recall, FM is better immune to noise or interference because the noise or interference basically distorts the amplitude level. So AM reproduction is relies on the amplitude. It follows the amplitude variation. If the amplitude variation is corrupted, it is distorted by some other noise or interference, your reproduction also gets different. But in the case of FM, it ignores the amplitude variation. Even if the amplitude distorts, it doesn't matter. It just follows the frequency variation, which is not much affected. So your reproduction is better. It is more immune to noise or interference. But the problem, you can see that you need wider bandwidth. Also, the FM radio receiver is more expensive. AM is very simple to implement. And to minimize the receiver cost, AM uses double sideband with carrier. It could also use single sideband or with, suppressing the carrier, but it doesn't, because when you have double sideband and the carrier, then you need the simplest circuit for reproduction. You can use just a diode and a capacitor that will reproduce. It's that easy, because diode, when you put it on the carrier, you get envelope on two sides, right? Probably remember. So with diode, you just cut off the negative side, and with capacitor, it follows the amplitude variation. so you can retrieve the information. So there's to minimize on the transmitting side, you're just transmitting once, so you can invest more there. But there'll be thousands or millions of receivers. So it is more effective that you try to minimize the receiver cost. So this was the motivation for the use of double sidebands with carrier for AM. And probably you know that AM radio was the earliest uh, broadcast uses, okay, for public uh, communication, for public information sharing. AM was the earliest method. Okay, now this is what I wanted to uh, explain. The principle is called superheterodyne. Uh, superheterodyne. That's the name of the principle, superheterodyne principle. And the radio receivers use uh, this principle. Uh, now you see that when you first capture the signal via antenna, the signal power is very low, and unless you amplify, you cannot work with it. So you need an amplifier next to your antenna. But for an amplifier design, if you support wide bandwidth, the gain is not much. The gain bandwidth product is pretty much constant for a particular type of amplifier. So if you bring about some changes, uh, it to increase the bandwidth, you have to sacrifice the gain. Now, for a radio receiver, it should be able to support the whole permitted operating frequency range, which is very large. Say for AM, you see that it is more than 1 megahertz, the total range. So the receiver has to support any channel, whichever channel is used in any country, should be audible. So big a range. Around this 1 megahertz range, a bandwidth of 1 megahertz is really large. Okay. Around 100 megahertz, 1 megahertz is nothing. But around 1 megahertz is a huge range. So if your amplifier has to support this wide range, its gain is gonna be very low. But you have to, yeah, I mean, before you capture, you don't know where the transmission would be. So the amplifier must support this wide range. This this leads to very low gain. Okay, but you have to bear with it anyway. But ultimately, you need to amplify with good gain. Otherwise, I mean, you cannot hear anything properly. So how can you manage that? You cannot ignore any channel, but you need at the same time good gain. Well, this is why another amplifier is used at the second stage, which can be used with a very small bandwidth, permitting very good gain. But how is it possible? You need to support all the channels. Well, yeah, the center frequency is shifted after this first amplification. The bandwidth is always say 4 kilohertz or say 10 kilohertz or 9 kilohertz. For FM is 200 kilohertz. I think the microphone is on for someone, which is causing some noise. Everyone, please uh, mute your microphones. And okay, let me try to find out this microphone is on. Okay, as you see, 106. 106 seems to have microphone on, and Iman. Iman and 106, please turn off your microphones. Do you hear me, Iman? Okay, I'm writing to him. 15. Okay, Iman has muted, so it is probably from 106. Okay, yeah. Okay, I don't know, but all microphones seem to be muted now, but we still have some noise. Okay, anyway, go back. Uh, the slide is visible, right? Okay. So the bandwidth is always same. The second stage amplifier, which is called IF intermediate. The first one is called RF or radio frequency amplifier, but the second one is called intermediate frequency amplifier, IF. That has a bandwidth of the signal bandwidth, like only 200 kilohertz for FM or 9 or 10 kilohertz for AM. So it can pass only a single channel. Okay. So what is done? All the channels are shifted to a particular carrier frequency after the RF amplifier stage, and this is done here. So there is an operation which changes the carrier frequency. It shifts the carrier frequency and brings it to a fixed value. And that is the center frequency of the bandwidth of this IF amplifier. How is it done? You generate another signal here, and the frequency of this generation depends, I mean, is variable. So you have a control. Well, when we capture a particular signal, particular channel, we tune, right? So there is actually a control, manual control, which shifts the carrier frequency. In the amplifier supports the whole range, all the channels it can amplify, but we tune to a particular region, particular, say, 9 kilohertz, 10 kilohertz, or 200 kilohertz, and that is allowed in the rest of the circuit. So there's tuning, we know. This tuning is coupled to this generation of the other signal. So the frequency of this signal is also varied accordingly. Okay, we'll use some examples for. Okay, we'll use some example here. The other generation is called local oscillation. I mean, you use a local oscillator. So this local oscillator frequency is taken this way. The carrier frequency is what you are currently tuning to. Maybe say you are capturing a particular audio, I mean, radio channel with center frequency 1 megahertz. Okay, so FC will be 1 megahertz. It could be something different when you tune to another station. So FC is variable, but if IF is a fixed number, it is for AM, it is 455 kilohertz. For FM, it is 10.7 megahertz. It is fixed worldwide. So now you see that if LO, this local frequency, I mean the frequency of the local oscillator is also variable. It changes along with FC. As I said, with tuning, you change FC, and that tuning operation is coupled to the local oscillator. So FLO also changes. And then you feed the two signals, this local oscillator generated signal and whatever is incoming. So think about the center frequency, FC. So what happens? You have a mixture operation, and which is pretty much like what we have in the case of modulation. This mixture operation generates two different frequencies. You remember that for amplitude modulation, you get new frequencies as sidebands in a way that your carrier frequency, then the information frequency, and plus the information frequency. This is one signal. And then one is carrier frequency minus your information signal, right? Carrier frequency, the upper sideband is carrier frequency plus information frequency. This is the frequency of the upper sideband. The lower sideband, carrier frequency minus the information frequency. So the mixture generates similar kind of frequencies. So FLO plus FC and FLO minus FC. But FLO was already FC plus FIF. So the two frequency you are getting, like FC plus FIF and FC plus FIF minus FC. Okay, so you're getting 2FC plus FIF, and the other one is only FIF. Once again, for FLO, you had FC plus FIF. So if you put that in here, you get as the output of mixture operation, two frequencies, 2FC plus FIF and only FIF. So they are far apart because FC is pretty large. So these two frequencies will be away from each other. Then a filtering operation removes the upper component, 2FC plus FIF. So you are left with only FIF. And that is a fixed number, 455. So now we see that the carrier frequency, which may be say 1 megahertz, is now shifted to 455. So other components around the carrier, okay, you have an say 10 kilohertz bandwidth around this carrier one. Other frequencies will also be shifted, but they will also take components around this FIF. So we have another 10 kilohertz component around 455 kilohertz for FM, for AM. Similarly, for FM, you'll have a 200 kilohertz bandwidth around 10.7 megahertz. So after the mixture operation at YT, you always have the AM bandwidth, 10 or 9 kilohertz bandwidth or 200 kilohertz bandwidth of signal, but around a fixed frequency, 455 for AM and 10.7 megahertz for FM. So the IF amplifier is allowed to have a small bandwidth, just as much as you have for the original information. So it can have a very good gain, and the rest of the operation is then safe. Okay. You would have to demodulate to get the original information, and then you filter out any unwanted components. You know that the reproduced signal should have a particular bandwidth, so all other frequencies will be that is at the low end. So a low pass filter will allow only this frequency then. So you have then reproduced signal. Okay, so we're almost at the end. One last thing we need to discuss. The other, there can be a problem with some image. Okay, there are some requirements like so I need to explain the image, which can be a problem. It is not, okay. It's easy to get rid of this problem, but it could be a problem. You see that if you have another signal also somehow getting into your receiver with, okay, maybe I use an example for explanation. We are uh, tuning to 1 megahertz. Um, so the local oscillator will be 1455 kilohertz. So then we are just using IF amplifier for further gain. But let's assume that somehow, I mean, there is also a transmission at 1910 kilohertz, and somehow this signal, this radio transmission is also getting to your circuit. So you will have the mixture operation, which generates signal adding 455 and also subtracting 455. Okay. When you subtract 455 from this 1910, you also get 455. Your actual desired signal is this 1000 kilohertz, and for which you are getting, I mean, this stage gives you 455. I mean, if LO becomes 1455, so from this 1455 operation, you will get uh, I mean, if some frequencies around 455. But another one, uh, you have at 1910 kilohertz and the radio station. So that is when subtracted, okay, is giving you the same 455 kilohertz component. So you are getting also transmission from another station. And so that will be an interference to you. Okay, so this is called image signal. So this could be a problem. This image signal could be a problem. So what you need to avoid the image signal is that, since superheterodyne principle is something that can be used in some other applications, you need to know what could be the problem involved. Okay, so it doesn't happen in our radio broadcast system, but to learn the principle, you also need to know what problem there could be. Um, mm, so the I mean, the radio frequency, uh, I mean, that you allow in the initially should be should have some limited bandwidth. Okay, it should not be larger than 2 FIF, so that you cannot capture any signal beyond that. If your frequencies, if you have a filtering which does not go beyond F2 FIF, then the image signal is filtered out, because you see that if I mean, these two signals are twice 455 away. That is why you have this problem. Okay, with the desired signal, it is, I mean, when you add, you get 1455, and from there you could get 455. But here you are getting also, because these two, 1000 and 1910, they are 245 away. So if you have a filtering like this, then this 1910 would be just eliminated. Okay. But of course, your bandwidth has to be larger than the audio bandwidth. Okay, so it says that it has to be larger than BT. Okay. Okay. Any questions? For FM, since it is 200 kilohertz away from 88 through 108, nowadays the smartphones also have FM receiver, and you can scan through the channels. Probably have noticed that it automatically scans at every 0.2 megahertz, starting from 88, and it goes up to 108. Okay. Do you have any questions? If not, we'll stop right here and move on to the next topic. Okay, we'll explain how data is routed for digital communication using an example. Uh, so the infrastructure and how it works uh, varies among the countries. So we are taking Bangladesh as an example uh, for the explanation purpose, but it is different in other countries. Okay. Uh, but I mean, probably you can get the knack. I mean, you can understand how things could be handled. Any example can explain the requirements. Well, but this whole discussion applies to digital communication. In the case of voice, in the case of, I mean, our previous discussion, radio broadcast had analog communication. The AM radio, FM radio, they all use analog communication. Your information is not converted into digital bits. So the analog form of the information is transmitted and recovered. That's the analog communication. But in digital communication, you first convert the information into bits and then you transfer. Now, within digital communication, there are two basic ways: circuit switching and packet switching. Um, so it may seem that in the switching cases, the bits are first packetized and then they are routed. And in the circuit switching case, you send the bits one after another without any packetization. This is a wrong notion. In digital communication, you always packetize the bits. You have to have some forms of packets. I mean, an understanding. Bits could be transmitted one after another. I mean, in one perspective, it can look like a stream, but there will be some virtual packetization. There will be I mean, the packet start at one bit and the packet end at some other bit. Okay, the next bit I mean, belongs to the next packet. So some packetization is always used in all digital communication system. So both circuits, although the term packet switching uh, looks like, I mean, different from circuit switching in terms of packetization. So both CS and PS uses packetized data. The difference is rather somewhere else. In the case of CS, basically, you reserve some resource for transmission, for sending the data. So you have actually, I mean, better quality of service. You can ensure that this communication path will be available whenever you have something to send. Okay. On the other hand, in the case of packet switching, you don't reserve. When you have no packets to transmit, you also have no path. I mean, you're not using any communication resources for transmission. And when you get some packets, you check if any resources can be made available. If it is, then just transmit using those resources. So conceptually, they are a lot different. in this case, since you did not have any prior reservation, you can come across a situation that you don't find any resources available. All resources are currently occupied. So then you have to queue your packets, and you may have more packets coming in. At some point, your buffer may overflow, and so some packets may be dropped. And when you get some resources, you can then start transmitting. Until then, these resources may still not be enough because you had no prior reservation. So you may not be able to send all packets. Some packets may have to be dropped. So the quality of service is not ensured. In the case of CS, since you have prior reservation of the whole communication path, and the capacity of this reservation path relates to the expected data flow. Okay, how much packets you may get per second is taken into consideration when you reserve the bandwidth or capacity of the transmission path or of the communication resources. Okay, so in this case, you can ensure quality of service. So now it looks like that CS is a better solution, but in fact, CS is getting obsolete, and everything is gradually becoming PS. Why is it so? Because in the case CS is not enough effective and enough efficient. When you don't have any, sometimes you may not have any data to send. But if you have prior reservation, it's a wastage. Okay, it's very luxurious that you're reserving, but you have nothing to send. Like the example I used before, that when a husband is talking to his wife, most of the time it is one way. So when if you have reservation of resources, the resources may be, say, in the case of 2G, it may be TDMA, FDMA slots. In the case of 3G, it can be some OBSF codes. So you are reserving some resources for communication, for sending the information. But uh, the husband is not talking anything, or he's not getting any chance to say anything. So there is nothing to send. I mean, this whole reserved TDMA, FDMA resources or CDMA OBS scores are just wasted. Okay. Sometimes he may just get a chance to actually to say that he agrees to his wife when he expresses uh, I mean, his agreement, he's agreeing. He uses a few bytes. So only then he is using. Rest of the time, it is idle, so it's not an effective solution. So this is why CS is not enough efficient. In the past, CS was it was all CS. I mean, it was mostly CS. It's because there was not too much uses around the globe. The total uses was limited. So enough resources could be accommodated or could be made available for whatever communication there was in the world. Now the whole world is communicating so much. There is so much information flowing. Unless you have a very efficient system, it will be beyond the affordability of people. Okay, so the efficient use of resources is now more important than the quality of service. Secondly, or I'd say more importantly, there are multiple ways now to ensure the quality of service when the quality is very, I mean, critical. Okay. Otherwise, you don't care the quality much. So there are multiple types of applications. So if it is very quality critical application, then there are ways to ensure the quality, at least to some extent. Okay. Now, so PS can be safely used for all purposes. Okay. So you can efficiently utilize your resources when you don't have any data to send, that you're not using any resource, somebody else can use the resource. So it is effectively used. Probably you have got the point. If it is not clear, please let me know. So you see that the packet drops can be negligible in CS, so quality service can be guaranteed. The up to 3G, CS is used for voice and SMS. And for all data purposes, is PS. But from 4G onwards, there is no CS. CS is no longer used in cellular communication. So from 4G, from LTE onwards, it's all PS. Okay. So voice, mm, uh, well, now I don't remember if I included it later. Probably I did not. Okay, then let me tell you that what is happening in our countries, the L LTE still supports only PS for its data part, but for voice there is no built-in solution with LTE. So it switches back to 3G when you make a voice call. And this is called, I write down the term, circuit switched fallback, CSFB, circuit switched fallback. So it goes back to 2G or 3G network, and it uses circuit switching as long as you are on a voice call. Once you complete the voice call, you will be put back to LTE. Usually, I mean, you can again start. It will put you back to 4G. Sometimes it can still keep you on 3G network if the 4G network is already overloaded. So
Sir,
yeah,
why can't we use the packet switching in case
yeah,
of the LT,
yeah, yeah.
in case
Uh,
of voice?
yeah. The problem is that uh, over several decades, a very strong and reliable network has been developed for voice calls around the globe. So there is already a infrastructure uh, working very well, and it had billions of investment. So for voice call, very nicely operating system is already laid around the globe. And overnight, you cannot come up with a solution for, this voice, which would perform with good quality. It would require definitely a lot of new investment, and to get, uh, I mean, enough good quality, it will, you have to ensure the performance everywhere, which will take a while. So what is happening gradually, people are moving to L, LT with voice support. So other countries, developed countries also started LT when they first deployed 4G. They did the same as we are doing today. They did the same. They used 3G, but gradually they set up the new system, investing again a lot. And nowadays in most developed countries use also voice on LTE network. In our countries, last year, they started uh, some operation of voice on LTE network in some limited areas only within Dhaka. So it is called, when you support voice on LTE, it is called VoLTE, voice over LTE. I'm writing down VoLTE. So VoLTE is now supported in our country, and from last year it has been supported, but only in a few limited areas. within Dhaka, in Gulshan, in Bosundhara, it is supported. Uh, so, but you need your phone to support VoLTE. Your SIM has to, you have to change your SIM. Your SIM has to support VoLTE, your phone has to support VoLTE, and the network also has to support. So we have to be within those limited areas. But if you can use VoLTE, then you'll see, probably you have noticed already that when you make a voice call, or if you haven't, then try it today. When you make a voice call, the network puts you to 3G. Okay. And after the voice call, it puts you back to 4G. But if you go there and if you use VoLTE, then you have a better experience. What is that? First of all, you can still stay on 4G network. So if you have some other data operation alongside, you're also browsing or you're downloading something while you're on a voice call, now you have better performance on data. Because when you're on 3G, your data will be low. You can use data services along with voice, but the data service quality will be bad. So as long as you have VoLTE, your data service will have good quality. Also, the voice setup, two more things you'll enjoy. If you is there anyone who is using VoLTE? Is there any student using VoLTE already? Nobody?
Yes,
Okay.
sir. I tried using it once.
Oh, really? So,
But sir, I switched my phone and the new handset didn't support it, so I
okay,
couldn't use it for very long.
okay. So how was it your experience? What was the difference? I'll tell you a couple
So
of difference, but before I tell you the differences, let me hear from the user. Okay, yeah, tell me.
sir, the call quality was better. So I mean, in normal times when there was no VoLTE, the the sound was not that crisp. It was not that clear. But when I used VoLTE, I found that it was much more clear and better in terms of reception quality. And other difference, sir, I probably didn't notice any other significant difference from normal 4G.
Okay, okay. Well, the call quality should be almost equally good because CS is primarily, uh, I mean, the key advantage of CS is the quality of service. Okay, so 2G and 3G offers pretty good quality of service. So in this may be a difference in our country, but in other countries, the call quality should be equally good. It can be expected to be equally good. In our country, the call quality was already not very good with CS. So when they deployed VoLTE, I mean, of course, there was enough care. So because of extra care, I think the call quality was found better in your case. Okay. But the call quality should also be good in 2G and 3G CS. So the difference should not be in the quality of calls. Rather, there should be two differences, like the call setup period should be very low. Very quickly, you can set up the call. In the case of,
Yes, sir. I noticed a difference
you
in
notice
that
this
case too.
difference? Okay, it should be, first of all, with CSFB, I mean, when we are on 2G and 3G, the call generation took a while, definitely. But now with 4G, it takes longer because first it puts you back to 3G. Okay, most of the time 3G. Sometimes I found it with 2G. Okay, I captured a lot of data with Xcal. So it puts you to 3G and then it sets up the call. Okay, so it takes a while. But in 4G, you can directly start making a call. I mean, only a few messages. I mean, some negotiation is uh, used at the application layer, so which can be very quick. So the call setup period will be much, much lower. So this is the primary advantage. Secondly, I mean, as I said, I mean, the data quality would be better when you have other services alongside. And another point is that as a user, you can make video calls even if you don't have any data services. I mean, we know that you need some data services for internet activities, right? Data package. You need to first activate a data package. You need to have mobile data on, right? And then you can have, say, on WhatsApp or Viber, you can have video calls. So video calls we can have, but with only mobile data services. But if you have your mobile data turned off, you have no data package uh, from your operator, you can still with VoLTE calls, you can still have video calls because VoLTE supports both audio and video. So it always uses the PS network. VoLTE uses PS network anyway, but you don't have to have mobile data. It is it will use PS anyway, and with PS, it will it can set up both audio and video calls. So with mobile data off, you can have video. Did you try it? Did you try video calls with mobile data off? You didn't, right? Okay, now you can try it. It should work. Okay, so these are the differences for team. Probably it's clear now, right?
Yes, sir.
Okay. Now, the way voice services work, at the bottom you have the operators like say Ruby, GP, and all other operators. And initially, when they first set up their networks, there was interconnection. So if you're a GP user and you're calling, I mean, the final point when they connect to outside is called gateway. So the gateway of Grameenphone was connected to the gateway of Robi. So if you're making a call, it goes via the gateway. That was the case before. Later means almost a couple of decades ago, uh, a government uh, initiated some government controlled node between the operators. So this is called ICX. So now the operators are connected via ICX. So if you make a call as a GP user to Ruby, the call would go via ICX. So these are some other operators. Okay. So some exchange through that the calls are routed. But if you're making a call to a GP user, of course, it doesn't have to go via ICX. It can go within your network. Okay. So between Ruby, ICX is not required. Now about international calls. If you're making an international calls, first it will be routed to ICX, then it will be routed to some operators which are called international gateway. So these are another set of operators. Now there are so many companies for ICX, for IGW. Okay, this is an international gateway or IGW. There are so many. In the beginning, there are only 4 IGW, including BTCL. There's always a government-owned license. Okay, and there are 3 other licenses for IGW in the beginning. Meet Telecom, Novocom. Okay, there are few. But now there are 28 IGW companies. Some of them have left operation actually. 28 licenses were issued, but some of them stopped operation. They could not survive in so competitive market. This 28 has been too many. So it will go via, when you're making an international call, it will go first via ICX, then via IGW, then IGW is has some negotiation, some deal with different international carriers. So these are some international carriers, okay, like British Telecom. Although I didn't list British Telecom, AT&T, they are also international carriers. So if you are making a call to UK, most likely it will be carried by British Telecom. What they would do, so IGW and IGW operator has say Summit. Summit is also now an IGW. So it has negotiation. Definitely British Telecom, AT&T are large operators. So I expect that it has negotiation with these international carriers. So your call may go to Summit ITW first, then it will be routed via this say British Telecom, and it will be taken to the node at the UK, and then it will be routed to their operator, and then to your friend. So you're talking to someone, and your voice packets are routed via all these nodes. Okay. So the international carriers will carry the signal. They are responsible for carrying the signal, and they will be using optical fibers or whatever medium they use. If they use some, say, satellite or something, they can. Okay. But nowadays, most of the things are routed via optical fibers, the undersea cables. That we'll explain also later in this presentation. And sometimes you have multiple carriers involved. Like if you are making a call to Latin America, so you may not find an international carrier, or you may not have, there may be, but you may not already have a deal with the international carrier, which can route up to that area, up to that zone of the world. So it will be routed to some node, and then another carrier will take it there. So the total cost will increase, because at the user end, you are ultimately paying for all these carriers. Okay. So multiple carriers, 2 or 3 carriers may eventually carry your voice packets and take it to the particular country. It depends on the IGW. Large IGWs have deal with more international carriers, and small IGW companies have few. So, I mean, with the large IGW operators are able to route more calls because of their deal. They get more calls. Okay, a larger share of calls they are able to route. So their revenue is higher. Okay. On the other hand, they also have to have some payments, okay, for deal with the international carriers. This is about voice calls. Then we'll talk about how the data is routed. So you see that these names are given by our BTRC. So IGW is not a name you would find in other countries. Okay, but you would find a similar infrastructure there. Okay, so this is just an example. If you work in other countries, you'll have some difference, but some similarity as well. Well, later, government inserted another node. Okay, now we have another node there sitting between IGW and ICX. It is called IOS, IGW Operator Switch. This is to prevent any illegal use of international calls. Okay, a lot of international calls were, routed without the knowledge of the operator. So there is some tax from the government. So this tax was easily evaded. This tax evasion was very common in our country. And to stop that, or to minimize that, this iOS has been inserted. So they monitor. You see that for local calls, iOS is not involved. It goes via ICX. But international calls have to be routed via iOS, and all iOS operators are under strict government control. So these are the iOS operators. Okay, they work very closely with the government, so they all monitor. Okay, probably you have heard that. Okay, so these are the reasons. Please go through this slide. I'd say, the multiple objectives they say, and I have listed all of what they say, but the key purpose is to stop any illegal international calls. Illegal calls mean, which has tax evasion. Okay. So you must have heard that some illegal VoIP calls are made. Well, VoIP itself is not an illegal technology. When you are making WhatsApp, nowadays we use, like, to talk with people abroad. We use voice, WhatsApp or Viber. This kind. So they all use IP. So IP, we will have further discussion. When it is PS, packet switching, you put it into, I mean, you create packets. These are called IP packets, and then you route. So voice are first put into IP packets. Uh, I mean, PS means that you have IP packets, and CS means there is no IP packet. You just okay. Now, the use of IP packets for voice is not illegal. You are doing it with WhatsApp or Viber, but those illegal VoIP calls have some illegal arrangement. They have some deal with someone at the other end, and the calls are routed, uh, avoiding the legal path. So you use some international carriers, or somehow you route the calls, but you have some deal in other countries, maybe in Singapore or somewhere. Okay, so there are other criminal people involved, and they take the share. So you route, but this illegal routing cannot be done in CS form. You have to use the packet switch network IP. So all this, I mean,
So we have another class at
another class. Oh, yeah.
10:30.
Okay. Okay, we'll go from here the next day. Oh, I need to take the attendance. Okay, everybody is present today. Okay. Sorry, I forgot that. Okay. Thank you. Thank you for your time.
Assalamualaikum, sir.